In this lesson, we'll be looking at continuous exponential decay. The formula we'll be using is P of t equals A times e to the bt. P is going to be the population of whatever it is that we're talking about. A is the initial population at time t equals 0. T is the amount of time in years that has gone by, and B is the decay factor. We're going to be using a Desmos graphing calculator, and I'm going to show you how I use it graphically to understand what's talking about, and also even algebraically, you can use this graphing calculator to make sense of these problems. So here's the context. This is about a population of bats, and this population of bats is becoming extinct. It says in 2015, the population was 2,000 bats, and in 2018, the population was 1,400. And we can assume that this is continuous exponential decay. And when it says create a model to predict the population decline, where t equals 0 is the year 2015, we're going to be looking for an exponential model where the base is e, just like this equation that we just showed you. Okay? So what I do to solve problems like this using Desmos is I first open up a new Desmos graph. So you go to desmos.com and open up your graphing calculator, and I type this text in as a note. So I'll show you what I mean. So here's the exact problem, and I added a note, and that's how you can type it. And then what I need to do is look for context clues and find two ordered pairs that I know will satisfy this equation. So it says t equals 0 is the year 2015. So I'm going to do 0. Oh, let me say this also. Another really important thing is you should then go and change your graph settings. So I have for my x-axis -1 to 30. For my y-axis, I think I kind of want to bring it up. I'll go down a little bit more. So -20. Well, I just like to see my axes. And let's do this also. Let's put a label there. So what is the x measuring? The x is measuring time in years since 2015. And I'm looking back at the problem for that. And what is it? What are we measuring? We're measuring the population of bats, this particular species of bats. And it's not in millions or thousands because I'm using the actual number. So the first ordered pair that's going to go on my table is 0, 2000. And how I added a table was just add a table. And when you do, it will give you this x subscript 1, y subscript 1 that automatically comes into play. So that's up there. And I think I want to change my graph so I can see that ordered pair a little bit more. I'll just make this a little higher. Okay, great. Now my second ordered pair is going to be 18, right? Because it's 2018. Oops. So that's 3 years past 2015. And the population is going to be 1,400. So I can see that this is definitely an exponential decay situation, right? I mean, it's never going to, the population will never get below 0, right? Which is why it is definitely not linear. And it'll never get back up higher, so it's not going to be quadratic, and we're assuming that this is continuously happening. So what we want to do for the regression model is we want to start with y1. Now when I type y, to get the subscript of 1, you could do shift dash, but you don't have to. With Desmos, you can just type the 1, and it goes down. It drops down to the subscript area. Now we use tilde to let Desmos know we need a regression equation. Tilde is that squiggle right underneath the escape key, top left part of your keyboard. Now we need A, we need E raised to the power of, B, and this is where we need x sub 1. Immediately, I can see this line that goes right through these points. I don't love the same color as my points, so I think I'll make it orange. So there's my exponential. These are my parameters. Okay, so my A in the formula that I'm using. This A and this B are given. So what I can do now is, since I need to solve problems involving this function, I want to write my equation in function notation. P of x equals, A is this 2,000, times e raised to the power of this B, which I have to just type in, and be careful when I type it, x. And I'm pleased to say that that went directly on top of the one that Desmos created, which now tells me that these numbers, I haven't mistyped them, right? So I'm now going to undo my regression equation and just use my function notation. So this is the population of bats in the year 2015, right? 0 years past 2015, it was 2,000. In the year So 3 years past that, I'm trying to grab hold of this. Okay, well, in 2018, the population was 1,400. And we can use this graph to answer these questions. Use the model to predict the population by the end of 2020. So let's think about it. The end of 2020 will be 5 years, right? So the population looks like it'll be what, 1,100 or maybe a little bit above 1,100? What we want to do is we want to say P of 5. And let Desmos tell us exactly what the population is predicted to be. So here's my sentence starter that I had written already. The population of bats in 2020 will have dropped to about 1,104 bats. Now I have another interesting question. According to the model, what year will there be fewer than 100 species? So the number 100 is down here. It looks to me like it'll be 25 years after 2015. So I'm thinking probably 2040. So what I want to do is let's draw a horizontal line at 100. Let's do y equals 100. And we can see that this, and I want to change my color here, we can see that these two curves intersect at an x value of 25.197. So based on just my graph, right, just my graph, I can say that in 2040, which is really 25.197, or 25 years after 2015, the population of bats will reduce to 100. Okay, so that's your graphical solution, just simply using where do these two curves intersect. But I want to show you how I use Desmos to solve this algebraically as well. And that's where I go up to what my function was and I copy it, just Command C, right? I'm on a Mac, and I paste it, Command V right here. And notice there's the blue, it's the exact thing. But instead of P of X, I really want the number 100 here, right? I want to know what X value will there be 100 bats remaining? And look, here's this blue line that is indicating the value of X that this will happen. But again, this looks like a graphical thing. I want to get X by itself. I want to solve this algebraically. So my next move is I copy this and I paste it. And I like to show my reasoning line by line. So in fact, I actually think I should start with that. And now, yes, I changed that to 100. Now I want to copy this equation. And remember, I want to solve for X. So to get X by itself, this 2,000 is on the wrong side. So let's divide by 2,000 to both sides of the equation. Okay, so I've done that. Now to get X by itself, it's up here as an exponent of E. So we're going to take the natural log of both sides, right? Because you know that they are inverses, right? So the natural log of E raised to some exponent is just the exponent. So on the right-hand side, this side simplifies to this exponent, which I'm just going to write down here. This left-hand side is a number, and I'm not going to bother simplifying that fraction. That's not necessary. Although you certainly could. I'm just not going to bother with it. Now, to get x by itself, I want to divide by this coefficient, right? So once again, I copy my equation. I am going to divide by that expression, that coefficient, or multiply by the reciprocal, right? So 1 over that coefficient. And there it is, exactly what we said earlier. According to the model, what year will there be fewer than 100 species? In the year 2020. So I hope that helps you see the value of Desmos and how it can really help you solve and make sense of these contextual real-life problems.